Hello everyone and welcome to section 2.3 where we look at stem and leaf displays. I know you're going to be very sad to see that this section is a one-pager, and sometimes I get complaints on email about how you paid full price for this class and you would appreciate 2 or 3 pages. Sorry about that. This is just kind of a short section. And actually, stem and leaf displays would normally just be included on our last section, section 2.2. So I don't know why the author put this particular type of graph on its own section, but that's what we've got. So kind of a short section today. So to start off, the book mentions something called Exploratory Data Analysis, or EDA. So I'm just going to mention that. I'm not really going to ask you anything about it, but if you happen to, look through the book, you'll see that the author mentions this in this section. It's just an approach to analyzing data sets to summarize their main characteristics. I'm usually using graphical methods, and these techniques are particularly useful for detecting patterns and extreme data values. So you could think of it like this. Exploratory data analysis, I'll kind of explain it just using other words. The note here, we could say we explore the data without any particular questions in mind. We just want to see how the data are distributed. So it's just, if you have a small set of numbers and you're just looking around, looking for outliers, are there any numbers that are really big or really small? Or are the numbers all clustered together? Just looking like that, just kind of barely taking a look. But while we've got this sentence here, how many of you are now thinking, data are? Anybody thinking, I like the sound of that? Anybody ready to jump from team data is to team data are? Maybe. Might have got a couple more. Okay. So either way, if you write data is, remember that's also just fine. So we cover 2 EDA techniques, exploratory data analysis techniques. We cover stem and leaf displays, which we're going to cover right now. And another one that you've probably seen before is box and whisker plots. And these are a lot of times covered in like algebra or some other math class. But we'll look at these in section 3.3. So today we've got stem and leaf displays. These are 2 of the main exploratory data analysis techniques. And a little note here, this is not super important. It's just a little extra information. Technically, histograms, which we covered, and Pareto charts. Remember, Pareto chart is just a bar graph in order from highest bar to the lowest bar. And technically, these are also considered exploratory data analysis techniques. Okay, and so some of this that we've just talked about is more than you're going to need to know. We just need to be able to make a stem and leaf display. Okay, that's the main point of section 2.3. Make sure you can take a pile of numbers and turn them into a stem and leaf display. That's what we need to be able to do. This exploratory data analysis little part I'm talking about is just some extra. Okay, we just need to be able to make a stem and leaf display and be able to read one. So a stem and leaf display is a method of presenting quantitative data in a graphical format to assist in visualizing the shape of the distribution. So we'll be able to see the shape of the distribution like we did with a histogram. Remember, a histogram showed the shape. We could have like a mound shape symmetric or skewed left or skewed right. So it shows the shape of the distribution of data. And stem and leaf display will do that also. So quantitative data, right? Quantitative, and the other one is qualitative or categorical. Quantitative, you could think of it like quantity, a number. Things where if you take the average or the mean of the numbers, it makes sense. Like the height of a person, right? If you compile the heights of people, those are going to be quantitative data points. Okay, so for stem and leaf display, we need quantitative data. And then here's some of the features. Shows the data in order from smallest to largest. Allows us to recover the original data if desired. That's kind of an important part. We can recover the original data, and that is like a dot plot. If you remember when we had a dot plot, each dot represented an actual data point. So the original data, sometimes referred to as the raw data, can be recovered from a stem and leaf display, just like a dot plot. So that's what's nice. So with a histogram, the original data are not shown. Remember, a histogram, you'll have a number line here, and you'll have a quantity up here, so you'll know, how many data points are between this number and that number, and this number and that number, this number and that number. You'll know how many data points there are by looking at the quantity here, but you won't have the original data. Right? So that's the advantage of stem and leaf displays and dot plots. The original data are all on display. Okay, so other features, it allows for easy identification of extreme data values, because we're going to see the data in order from smallest to largest. So if there's one that's real extreme, we'll be able to see it easily. The shape of the data distribution will be shown. So we can have things like mound-shaped or skewed left, skewed right, pretty much like a histogram. We'll have the shape of the data. And then it's useful for moderately sized data sets, 15 to 150 data values. You don't really want to use a lot of data, and really a stem and leaf display is one that you'll see the least. Stem and leaf displays are still taught in pretty much every stats class, but I see fewer and fewer of them in reality. So you may not ever have to produce one, but it is nice to just be able to read one if you do see one. Okay, so they're not used as much, but they're for moderately sized data sets. You don't want to have 1,000 data points in a stem and leaf display. And became popular in the 1980s. Just like dot plots, they were both popular in the 1980s because the computer printers of the time, those dot matrix printers, could easily produce the graphics. So back in the bad old days when we had dot matrix printers, you could basically make any design you wanted if you could make it out of an asterisk. And some of you may remember those days, I do, when everything you created graphically on your computer printout was made out of one of these, so a little limited. Okay, so they often when these are used, they'll be done by hand for a small set of data values just to kind of get a feel for where the data are, which is convenient for us because in the first year stats class, we'll do them by hand also. Now, I have to make a little note here. There's one of the homework problems going to ask you to do something that is not possible. So in the homework number 5B, for those of you who have the hardcover, or who actually have a copy of the physical textbook, it's on page 75, and ignore something. It's going to tell you to do something you have to ignore. Ignore where it says use 2 lines per stem. Okay, because you can't do that. You can't do it. So ignore this part in homework number 5B. It's going to say use 2 lines per stem. Ignore that and just do everything else. Okay, so what we're going to do for this is pretty much the handout. So what we're going to do is just do one of the problems, and I'll show you how to make them work. And then the rest of the homework problems are very similar. So what we will do is first I'm going to kind of show you how to get started just with some scratch work. Okay, so what we'll do for this one, let's look at section 2.3, problem number 2. And for those of you with the book, it's on page 74, but it's section 2.3, number 2. And this problem gives us 48 numbers, and here's what the problem says. It says, wetlands offer a diversity of benefits. They provide a habitat for wildlife, spawning grounds for U.S. commercial fish, and renewable timber resources. In the last 200 years, the United States has lost more than half of its wetlands. Environmental Almanac gives the percentage of wetlands lost in each state in the last 200 years. And they give the data for the lower 48 states. They give the percentage loss of wetlands per state. So they give us the 48 numbers, and then they ask us to make a stem and leaf display of the data. It says, be sure to indicate the scale. How are the percentages distributed? Is the distribution skewed? And are there any gaps? So to get started on this, so there's going to be a little bit of scratch work just to get started. So let's just make a little note here. We need to note that the data are from blank to blank. In other words, we want to find the smallest number and the largest number. So we need to look through that pile of numbers. There's 48 numbers. And if you look, it looks like the smallest number is 9 and the largest number is 91. So if we're going to use a stem and leaf display, we're going to need to make our numbers have the same number of digits. So in other words, this 91, this is a 2-digit number. Can you think of a way we could kind of force this to also be a 2-digit number, the number 9? And you might be thinking we could do this. Let's consider this 09 and this 91. So we'll say that these numbers go from 09 to 91. And the reason that we need that is because of the way stem and leaf display is set up. So when we do that, we'll have our stem here. Again, this is just scratch paper, but it'll give us an idea of how this is going to work. We'll have our leaf here. And what we could do with this, we could have the stem consist of the tens place. So the tens place, so like from 0, and then 1 for the numbers in the teens, 2 for the numbers in the 20s. We have to go all the way to the 9s. So what we would do is set up our stems like 0, 1, 2, 3, and we go all the way to 8 and 9. And then the leaves would be the individual ones places of the numbers. So for this number, 09, the leaf would be 9. So when you read a stem and leaf display, we would read this is a number 9. So let's say there's a number 17 in that list. Then they would have a 7 here. And then let's say there's a 18. What if there's another 18? We just put another 8. So the way we would read these numbers is this is the 10s and this is the 1. So it'd be 9, 17, 18, another 18. So when we list these out, we'll list them in order from smallest to largest. So let's say there's a number 20 in the list. We put a 20 here. And we just go right down the line until we have 48 numbers. So the last number, 91, we'll have a 91 right here. And then we'll just fill all these in with the numbers in the list. So that's pretty much what we'll do. So for each one of these, we just have to look and see, okay, how are we going to start? We need them to have the same number of digits. So we do something like this. And then we can make, with 2 digits, which almost all these are going to be, we can set it up this way, the 10s. And then the leaves will all be these individual ones. So if you're not quite sure what we're doing, you'll see in a second. We're gonna actually do this problem now that we went through this, so you can kind of see the basic idea. Now we'll go through and we'll just do this problem. Okay, so let's make a little room here, and what we'll do is we need to have room for a title. So let's go like this. Let's have, for the stem and leaf display, we have a vertical line that's going to separate the stem from all the leaves. And then we'll have a little, we'll have a horizontal line up here. And I'll fill in some details later, but for now, if we start listing the data, we've got a 0, 9, that's our smallest number. Now, if you look in these numbers, on problem number 2, there are no numbers in the teens. There is no 11, 12, anything like that. So when I put the 1 here, there's nothing to go with it. So let me just count the rest of these down. 2, 3, 4, 5, 6, 7. We need to go all the way to 9. 8, 9. And then we just fill in. So if you look through that list of numbers, and we're at a spot, again, where it's going to be a little tedious because we're doing this by hand, but you look through that pile of 48 numbers, and you will see the number 20. The number 20 is in there. Then you'll see the number 23. There's a 24. And like I said, you just go through them like this. It's a little tedious, but eventually we'll have them. But look what I'm doing. I'm spacing them evenly, because here's what you don't want. You don't want to have, like, let's say there's just these numbers in the 20s. Then you do the 30s, and you're like, okay, there's 31, 32, there's another 32, there's a 33 and a 35. So if you first look at it, this is going out further. So we're going to use this to show how the data are distributed. So there's actually more numbers here than there are here, but at first glance it looks like there's more here. So what we need to do, we need to make sure we space these consistently. All right, we're doing it by hand. Not going to be perfect, but we can do it pretty good. So if you continue looking through that list, you'll see there is a 27, another 27, and then a 28. Then on the 30s, there's a 30, a 31. There is a 33. There's 5 35s. And a 36, 37. There's a lot of them in the 30s. A couple of 38s and a 39. In the 40s, there's a 42, another 42. There are a few of these 46s. There is a 48, a 49, and a 49. And then the 50s, there's quite a few in the 50s also. There's a few of the 50s, a couple 52s. There's a 54, 56, 56. In the 60s, this is where it starts dropping off. There's a 60 and a 67. And that's about it. And 70s, there's a 72, 73, 74. And again, these are just coming out of the pile of numbers. We should have 48 numbers when we're done. In the 80s, there's an 81, 85, 87, 87, 89. And then there's a 90 and a 91. So these represent those 48 numbers, right? There's a 20, there's a 23, a 24. There's two 27s. That's how we read these. So this is the stem here. This is the stem. All of these are the leaves. And sometimes when I see these, people will actually write stem here and leaf here. You can if you want. I'm not going to, but you can if you want to. But what we need somewhere is a key. We need a key so that people know what these are, right? That We need to know what these are, how to read it. Like, is this 2.0, 2.3, or is this like 4 foot 2 inches? We need a key here. So what we'll do, I'm just going to put a random number up here. It could be anything at all. Okay, make sure you're paying attention to this part. This can be anything at all, because this always causes confusion. It can be anything. You can pick a number from in here or just totally make one up. It does not matter at all. It's just a key. I'm going to put 43. Could I put 17? Yes. I could put 26. You could put anything you want, but we need a key. And I'm saying what this equals. This equals 43%. That is called the key. I'm going to write this in red. This is the key, and we need this. We need this, okay? Now the stuff I'm writing in red, you don't write that on your on your actual graph. But I'm just pointing out the fact that every one of these, when we make a stem and leaf display, we need a key. I've seen some people write them off to the side also. But this is how our book teaches it. So it's just easy up here. Now we know, okay, these are percentages. This is not 42 cents. It's not 50 polywogs, right? It's 50%. So these are percentages. We still don't know what it means because we still need our title, but we have the key. The key tells us what these are. These are all percentages. And then the title should take care of the rest. And let's see. And one thing you notice too, sometimes the way the author does it in the book is different from the way they're done in the answers. And that's common in textbooks because a lot of times the authors will be working with their students. A lot of times they'll be the graduate students who will work on the answer keys, so sometimes there's variations. So the book, the back of the book puts this line here. The examples in the book don't necessarily do that. So you can do what you want. I think it's a little easier. And I think when I do see these, which isn't very often, but when I do see them, I typically do see a line here. So you can handle that however you want to. But for sure, we need a key. We need a key. We need a title. So let's move up here a little bit and put a title here, and basically just have to say what these are. 43% of what? So I'm just going to write something like percentage of wetlands lost in lower 48 states. Okay, so there's the title. We always need a title. Remember, you guys promised you would never call it title, but we need a title. And we need a key, and then these are all the data. One other thing to notice, you guys remember a long time ago, you would have learned in algebra class the order of operations, and you probably learned something like, please excuse my dear Aunt Sally, or PEMDAS. Well, the reason that you learn this, and everyone on this planet learns some variation of this so that we all do things in the right order. So math is said to be a universal language. So if you are in Ohio or Michigan or Tokyo or Russia, and wherever you are on this planet, we will all get the same answer to arithmetic questions because we agree to do this order of operations. So it's sort of like that here too. So sometimes students look at this and they're like, it's kind of ugly. I'd like to put commas in here or put boxes in here. We don't want to do it. We want to do it just like this so that even if it's kind of plain, everyone who has learned how to work with one of these can read it and get the same thing. So for now, we're in a first year class. Let's just do it so we all do it the same way. and then we have no problems with any kind of confusion. Okay, so another thing is you can see how the data are distributed in this graph. It's like a histogram vertically. So if you look at this like a histogram vertically, look how the data are distributed. They kind of go like this. So this one, if I had to describe this, it doesn't fit anything well. But you can see the distribution here. I mean, it's kind of mound-shaped, but not perfect, right? But somebody could say it's kind of mound-shaped, or maybe you could even say slightly skewed right, but it definitely doesn't fit into anything perfectly. You could even mention maybe the data are concentrated from 20% to 60%. There's a lot of them right in here. But it's like as far as, well, you can see all the actual data points are here. This is 23. This represents percentage of wetlands lost in the lower 48 states. So some state lost 91% of its wetlands. But so you can see the actual data, and you can see the shape of the data set. If you think of this as like a histogram on its side, you can see this shape. So go ahead and give it a try. There's just a few problems. They're going to have you practice making these stem and leaf displays, and they'll ask you questions about them. And if you have any questions, of course, let me know.